Light travels through a vacuum at a constant speed of roughly 300 million meters per second. Without interference, it follows a perfectly straight path. That straight-line trajectory breaks the moment light enters a denser medium, like water or glass. This change in density slows the light down, forcing its path to deviate, a physical process known as refraction. By shaping glass into a specific geometry, we create a spherical lens. This allows us to harness refraction, dictating exactly where and how severely the light will bend. Depending on the curvature of the glass, a lens performs one of two primary functions. It either converges the light rays, bending them inward to meet at a single point, or diverges them, spreading the rays outward. To measure this bending accurately, we define two reference markers. The geometric center of the lens is called the optical center. The straight imaginary line passing directly through the center is the principal axis. Optics is the rigorous study of these forced deviations. By manipulating the physical shape of the medium, we compel light to abandon its straight-line nature to form images of the world around us. Calculating the exact degree of refraction requires a standardized coordinate system to establish precise physical directions. Under the Cartesian sign convention, the optical center sits at the origin of a grid, with the x-axis as the principal axis. Incident light always moves from left to right. Distances measured in this same direction are positive. Opposite distances are negative. The vertical axis follows standard graphing rules. Heights measured upward from the principal axis are positive, and heights measured downward are negative. By locking distances to a coordinate plane, the physical direction of the light's bending is automatically embedded into the math. The sign of the final calculation tells us exactly where the light is going. How do we assign a quantitative value to the strength of a lens? A relatively flat piece of glass will bend light gently, causing it to converge far away. A highly curved piece of glass forces a sharp, immediate bend, converging the light over a very short distance. We define this ability to introduce deviation into a beam of light as the power of the lens. We can derive the exact formula for power using basic geometry. Consider a single ray of light approaching a lens parallel to the principal axis, striking the glass at a specific height we will call h. To standardize our measurement, we apply a unit distance constraint. We set the incident height h to exactly 1 meter from the optical center. As the ray passes through the convex lens, it refracts downward, eventually crossing the principal axis at the focal point, f. The distance between the lens and this point is the focal length, f. The angle at which the light was forced downward is the deviation angle, delta. Notice that the optical center, the focal point, and the point of incidence form a right triangle. We can solve for the deviation angle using trigonometry. The tangent of delta is equal to the opposite side, our unit height of 1, divided by the adjacent side, our focal length, f. Because optical lenses deal with very narrow angles, we apply the small angle approximation.
When an angle is small, the tangent of the angle is effectively equal to the angle itself. Therefore, the power, P, equals 1 divided by f. The power of a lens is literally the inverse of its focal length. The shorter the distance required to focus the light, the higher the power of the glass. In practice, we measure this inverse relationship using the standard SI unit known as the diopter, represented by a capital D. 1 diopter is equal to an inverse meter. When an optician writes a prescription for plus 2.5 diopters, we divide 1 by 2.5 to find the focal length, plus 0.4 meters, or 40 centimeters. The positive sign indicates a convex lens that converges light. Conversely, a prescription of minus 4.0 diopters yields a focal length of minus 0.25 meters. Here, the Cartesian sign convention dictates that the negative value requires a concave lens, which diverges light. A negative focal length means the light rays never actually meet on the right side of the lens. Instead, they spread out, appearing to originate from a virtual focal point located 25 centimeters behind the glass. A single number on a medical prescription contains a complete geometric map. The magnitude tells the manufacturer exactly how sharp the curve must be, and the sign dictates the physical shape needed to correct the eye. High-precision imaging often exceeds the physical capacity of a single lens. A solitary piece of glass cannot introduce extreme deviation without causing severe distortion.
To solve this, opticians place multiple thin lenses in direct contact. The light passes through the first lens, forcing an initial convergence, and then strikes the second lens, which refines the path further. Because power is an inverse metric, it scales linearly. The total optical power of a combined system is the algebraic sum of individual lenses. P equals P1 plus P2 plus P3, and so on. This addition rule allows engineers to be highly specific. By stacking a high-power convex lens with a low-power concave lens, they can subtract total power to eliminate color fringes and refine the sharpness of the final image. Combining lenses transforms single pieces of curved glass into custom optical engines capable of achieving magnifications that a solitary lens could never physically support. The ultimate application of combining focal lengths is the astronomical refracting telescope. Its function relies on the mathematical ratio between two specific components, the objective and the eyepiece. The large objective lens gathers light, gently converging parallel star rays to form an image inside the tube. Opposite, the high-power eyepiece captures this image, sharply bending the rays to drastically magnify the angle for the human eye. The magnifying power of the telescope is calculated by dividing the focal length of the objective lens by the focal length of the eyepiece. This creates a direct mechanical trade-off. Swapping in an eyepiece with a shorter focal length increases the system's magnification, allowing you to see finer details, but physically narrowing the field of view. By defining the geometry of a single bent ray and translating that deviation into a standard unit of power, we built the mathematical foundation required to see across the galaxy.